welcome home, welcome all. I'll make this short presentation on which is entitled ESP firmware update over the air, OTA, secured by Azure Sphere. I did a presentation of Azure Sphere in the previous live embedded conference. So I added, you can see that on the video that was recorded. Still, I prepared a small introduction on this just to set up words and things. Okay, so it's I think today we have at least three talks about OTA. I think it's an important subject, and it's pretty tricky. So let me first introduce myself. Co-founded Theoris. I do embedded software since the mid-80s, and co-founded Theoris 2002, 20 years ago, still there. I do teach a lot. Well, I spend part of my time teaching both, well, mainly system programming, both on Windows and Linux systems, plus real-time and embedded stuff through RTX, which is a Windows add-on for real-time, Micro EJ, which is an embedded environment for developing application on microcontrollers, and FreeRTOS, you may also know about. I did co-author a book published in by Wiley a few years ago on a real-time embedded system that does not exist anymore. Let's say that it's not supported by the main editor, who was Microsoft. Yes, things are changing in our domain, and I still contribute to some industrial projects. So the agenda, the Azure Sphere solution, I'll just explain how it works, well, which are the concepts, speak a bit about OTA, pros and cons, and what we have on the ESP side. Espressif did a good job in the domain of software, I think. They're not the only one. STM32 did a pretty good job too in the side of software, but ESP's provided first in 2013. They provided open source, the complete open source base for their devices, chips, and this allowed us to do a good job on it. And this may explain why we find them quite everywhere. And then I'll explain how we did OTA with Azure Sphere for ESP. And also in this original solution, we provided update control through another Azure solution, but it could be any cloud solution. This one is not dedicated to Azure, but it allows to control the update through another channel once it's been secured. We'll see that during the press. So Azure Sphere is about computer security. Azure Sphere is a secure hardware and software solution proposed in a package. Well, it's a complete standalone package that covers all things needed for computer security, which we could just put in a nutshell with this phrase: I know my bits. Okay, I have a complete controls on every byte that is in my machine, every byte and where it is. Well, it's basically, it's the only way to control a computer. I know all my bytes. I know all my bits. And I must admit that nowadays, either on Windows or Linux, this is not an easy task if we consider the width, the complexity, everything that happens. Still, smartphones, for example, are a good example of something that is pretty well controlled. Another example is the set-top box. So computer security has been set up by Microsoft in what they call the 7 properties. They have, technically speaking, set up 7 different elements that have to be addressed in a so-called secure solution. It's, well, hardware root of trust. Well, it's the very beginning, okay? A computer is safe as long as the power is off, isn't it? As soon as the power is on, it's not safe anymore because it's running stuff. So can I be sure that from the first instructions, things are under control? Then defense in depth, even if somebody can breach the defense, does it has a complete impact and the whole thing is open, or do we have layers? Do we have a construction that allows me to accept breaches? The best image I have on this point is the fortress. Any fortress you can visit that has been built between Middle Age and even the 19th century. If you take a look at them, they have walls and walls and walls, defense in depth. Small trusted computing base. Is there a place where I have a full control because it is limited? It has a small footprint. Relates to my first remark on how can you control something that, when it installs, occupies 10 gigabytes of my disk. Dynamic compartments. So how the barriers are set up and how can I configure the barriers? Basically, if I presented the images of the walls in a fortress in the second point, this fourth point would represent for me, the bridges and the doors, the grids that you can open and close. So the defense in depth should allow you to set parameters and decide for your own usage which one you activate and in which condition do you activate these. A very important element as the fifth, passwordless authentication, because password means human. And, I've learned very soon that the problem is always between the keyboard and the chair. And when people decide to build security on user password, it's a way to throw the huge problem in the hands of people who are not aware. And basically, our memory hasn't been built to remember passwords. So it's leaked by design. I mean, nowadays we all notice that we have all the websites, they banking systems, you have to enter 3 different passwords and 2 codes that were sent through SMS. Well, we see the limitations of that password authentication right now. Well, it was easy to spread software around, but it was very dangerous, and now we are getting to it. So we have to be passwordless. Error reporting, very important. The system shouldn't be silent. We should be aware of what's going on. We should be aware on attacks. We should be aware on function call that failed. We should be aware of compartments that have been tried and failed, entries, network activity. So the system needs a channel to report errors, and last but not least, update. Okay, because no system is perfect. So first, it's your app. Even if you developed an app that has been settled, even if you did put the right parameters on your defense in depth, you may have made mistakes, or you may be able to enhance what you've done. So you should be able to update easily. It's all a matter about OTA, update easily. And even bigger than this, even the OS, even the platform should be upgradable. So renewable security is something that is the basic element of any system, and especially connected systems, because for sure connected systems are reachable, ways more reachable than embedded systems, but not even systems that are not connected, connected to the web, or so may also have weaknesses. People could temper them or whatever. So you need to be able to update anyway, easily. So how does Microsoft build? How does Azure Sphere build their solution on these 7 elements? The blocks are: first, certified hardware. Basically, it's a Microsoft IP and Microsoft software. Well, IP at this hardware level. That is the encryption and vault elements of the solution. Anything that relates to saving and protecting the secrets. Let's put it this way. Very important for the root of trust. So Microsoft has published this IP and works with chip manufacturers to, well, chip conceptors to integrate that IP in different chips. I think it's now even part of Intel, some Intel chips. Okay, so it's sort of a secure zone inside the chip. But it has been designed to work with the whole Azure Sphere stack. This is where it's different from usual secure elements or secure hardware provided in other hardware solutions. This certified hardware comes from the experience of Microsoft in the domain of Xbox deployment, which is a system that is on the field, that is to be updated, and it brings money to the company, so it has to be secured. The other brick, which builds upon the certified hardware, is a dedicated OS and software. This is the fortress. This is the thing that has services where you can build your own solution and set up your own protections, put it this way. So 1 and 2 built up a platform, an embedded platform where you will develop your apps. Then this, I said, was not standalone. It's connected to a cloud service, a cloud infrastructure, which is the Azure Sphere Security Service. It's an enforced solution at Microsoft that will handle the life cycle of these devices in the field. We'll see that. And this service has a user interface. This is why I put the laptop there, because you will access Azure Sphere Service to control your devices on the field if they are Azure Sphere devices. So the certified hardware, some chip manufacturers have already provided things for that. So it's made of different elements, including the Pluton part, which is the original thing. And you should notice that we have a network connection in there, which is inside the chip and not outside. The software itself is based on the bottom left, in the middle of my slide, a custom Linux kernel that has been redesigned by Microsoft to be a small base. It's a 4 megabyte Linux kernel that is embedded in the Azure Sphere operating system. It's part of the Azure Sphere operating system, and it will allow developers to use a custom POSIX API to build their apps. This is what we've been using. You see to the right, the Pluton security subsystem, and to the left, we have the developer experience that is provided with that, including Visual Studio and Azure Sphere SDK and communication service. So this is the interface. This is what you have as a tool to manipulate your devices on the field. Okay, pretty important. In Azure Sphere, you have 3 concepts. The concept of device with a unique number, the concept of tenant that associates an identity with a device once in the lifetime of a device. One very specific element of Azure Sphere is that every device will be associated to one tenant only during its whole lifetime. Okay, you burn the device. It's a very important step. So the life of the tenant and the life of the device belong together. And if the tenant says this device is out of role, the device won't run anymore. It's just one way of handling one critical element about lifetime of embedded devices in the field. Then you have a third notion, which is users, other users, people who will be able to manipulate, develop software, publish software to that device, and query information about the devices. Okay. So here is how things work in Azure. Chip makers build chips with unique identifiers. These chips are embedded by an OEM to build the board. Then these chips have unique IDs provided by Azure. And as soon as they are manufactured, they are known by Azure, still not in operation. Now, on the other side, you have people, users, belonging to an Active Directory. They need an identity in an Active Directory, which is either academic or enterprise. And the first step is to create these tenants that will lock the devices for operation. At that point, devices operate. Now, either the administrators of the devices or dedicated contributors to the devices will be able to publish software package and update and manipulate the devices. Now, let's talk about MCU update over the air, OTA. Nowadays, we know we say OTA update, we say OTA, that's enough. Pros and cons. When connected device, use the network for update. Well, that's obvious. I think the first device I've had is my set-top box. As soon as you deploy set-top box, or if you're a telecom operator and you deploy set-top box in the field, you need to control what's in there. You know you'll have to update. You know you'll have to do many things. So they have deployment infrastructures. It's an automated service, no auto interaction. Many examples I just gave them. Well, this is the pros of it. The problems are critical components. Dedicated storage organization. You need to duplicate this The flash, you need some extra flash. Maybe you need to keep two versions in order to be sure that if you fail on it, you can still roll back to the other ones, many elements. You may even decide to create your own bootloader for that, dedicated bootloader that knows about update. It's a very common element. All these require development, certification, a lot of things, but the biggest thing is about the secure protocol. How do you drag the bytes to the device? And the problem here is that you need a dedicated infrastructure. Okay. If I take the example of OTA provided by Espressif, okay, they have an OTA library. It's pretty well built. HTTPS OTA config, HTTP OTA handle, OTA complete, perform, finish, abort, data received, and other functions. This is quite complete. Now, if you read the documentation provided by Espressif, you'll have a notice about security that as in the process of being updated, the device may be violently hacked. I think it speaks for itself. So you have to develop your own software that controls these things at the protocol level. OTA issues is all about security for sure. Firmware bytes should be sent securely. Cipher algorithms, program cipher component of the MCU. I'm talking about security IPs, encryption, and SHA, well, whichever cipher calculus that has been embedded in the hardware. Well, it's provided through registers, so you have to develop software to call these guys. And as you develop software, you may build holes in the security protection. You may build holes in the wall. And all these things should be validated before deployment. It's a big constraint. The biggest one. Credentials should be under control. The problem is that as soon as you set security, you have to some people know, some other people don't know, and they don't have to know. Okay. It's the thing about secrets, you know, in the kindergarten, you say, what is a secret? A secret is something that you tell everybody not to repeat to somebody else. Okay. Well, this is the definition of secrets in many situations I've seen on the field, where if the final person using the device doesn't has the admin password, he's not able to do that thing or run that stuff. Okay. The manipulation of credentials is a big problem. Nowadays, you buy a car, you choose the password to control the car. Now you sell the car. What about the password? Okay. How can you be sure that all these credentials have been removed? And I don't want everybody to, obviously people are ruling the devices, people are ruling the software, and I don't want all these people to share the same responsibilities, because they don't have the same agenda, they don't have the same responsibilities. So how could we separate things between the send update and the apply updates? Okay. This is one big point about the solution we have built here. And we need a cloud infrastructure, not only an HTTPS server. All choices. OTA shouldn't be an MCU library because, well, the main thing here is that I don't want to spend money in developing secure software, okay? Because I have to develop it and I have to validate it. Too much, way too much. No specific bootloader, no constraint on memory footprint application. I want to keep my MCU plain, pure, pristine. OTA transfer is performed through an Azure Sphere device, okay? Secure Azure Sphere network connection and platform. MCU firmware is a payload inside the Sphere update app, Yes, this is the main idea. Some constants in my Azure app will be my MCU firmware. And then we don't speak about OTA anymore, because OTA is a native Azure Sphere security service. Still, I can send my bytes securely, but I want to open the control of the update to a population that is wider than the population that handles the device. You remember identity credential separation. Then we will update through a service that we implemented on Azure IT Central, because it's easy and goes fast. It could be any AWS or whatever. MCU update is on demand by the Azure Sphere application. And several MCU firmware are available in the payload. You may choose the one you run through this. So send an update or separate it. Tenant is not necessarily the user. Okay. This is the general architecture. You see to the left the ESP device connected through the Azure Sphere device, controlled by Azure Sphere. We have the Azure Sphere interface on the top in the middle to do the app updates and MCU firmware that will go directly in there. And then we have the other interface, IoT Central, that allows me to see what's going on and decide that I update my device with something that has been validated. So this is the hardware for it. We have also developed the interface to a small LiquidCrystal just to display what's going on there and have some information locally on the device. So this is the hardware interface we've used from the Azure Sphere device. Not much power, because as you see, the only power supply comes from the right here. So the whole thing is powered by the device. Then the Azure Sphere device. Then, sorry.
Thierry?
Yes.
Sorry. It seems like your slides are not still displayed.
From the beginning?
No, not from the beginning, but for till maybe 10 minutes or something like that.
Okay.
And I was listening to your presentation, but not watching, I have to say. But so.
Okay. Oh, the screen share has been. Okay. Let me try.
Okay, it's good now.
Oh man, the screen share can die because I did move the button outside my field. I'm very sorry. So what do we have here? When did it cut? 10 minutes. I think that was displayed. Yips. Do you have any message on where did it cut? 10 minutes. I think I was well, let's go to the most important elements. First, the global architecture, which displays the ESP device, the Sphere device controlled by Azure Sphere, the Azure Sphere interface. I'm going from the left to the right. The Azure Sphere interface that allows me to control what goes to the Sphere device. And then the Azure IoT Central device interface, sorry, that allows me to check what's come from my device and decide which software should be, well, which firmware should be updated if required, okay? This is the view of the hardware that you didn't have. That was too bad. You notice that the whole thing is powered to the left. And here, here is the schema of the hardware. We use, well, one I2C and voltage for the small LCD display. And then we have one serial line 0 to do the download to the ESP device, plus 2 GPIOs that allow us to control the reboot and decide that the reboot will be for flash, will be for tool anyway, flash control. This is allowed by the ESP bootloader firmware. So the Azure Sphere software, we had to port LiquidCrystal library, ported to Azure Sphere POSIX. We had to take the ESPtools library, which is C++ also, and port it to POSIX Azure Sphere, including file handling, because yes, the 4 megabytes Linux inside Azure Sphere doesn't have a file system, but it has a notion of resource that allow you to embed resources. And also the UART is special in terms of interface, because there are no threads either, an event-oriented queue. So this was porting, and then the application development that will include, well, basically IoT central interface plus MCU firmware. So here we have what is provided by Azure Sphere to the device: GPIO control, UART, I2C, Sphere network interface, and we have around the hardware and the cloud. You may notice that we are in an embedded conference, and this is why the cloud is on the bottom and the hardware is on the top. I'm pretty happy to achieve that in a slide. So now the app, we have the ESPtools port and LiquidCrystal port that we will publish on the Azure Sphere GitHub one day. And the whole app, which has ESP flash control, telemetry protocol. We had to develop a dedicated protocol with the ESP application to talk and get the data. Once it's updated, LCD control, Azure IoT interface to receive orders and publish. So we can both send firmware to the ESP and talk to it through its protocol. And then we have the cloud interface that will provide both update of the app when we want to update the app. Remember, it contains firmware 1 or firmware 2. We have 2 versions of the firmware, which have different functionalities. And also the fact that automatically, as I have an Azure Sphere device, the OS will be updated automatically. This is the blue arrow, if required. Microsoft decides that. And IoT Central is a web interface that will allow me to discuss with my device through Azure Sphere. So the tenants here.
Thierry, yes. Time is running very fast. And
okay.
How many time do you have?
2 slides.
2 slides. Okay, 2 slides, but no more.
No more.
Because after we have another talk.
So here are our tenants, products, and role. We have created 1 tenant, Theosphere, 1 Azure product, ESP updater. We have several people as administrators that can just publish software to these devices. So this is the send part using exclusively Azure Sphere interface. And then this is the update part, which is this IoT Central interface standard, where you can see your telemetry information, and you have 2 buttons to say update to the DHT version of the software that will just provide telemetry data, or update to the LED interface that will let the device flash 2 LEDs just for demonstration purposes. Here we are. Thank you. Sorry for the delay and the little problems we had with my presentation going through. I'm done.